I find this unit wonderful and fascinating, but I'm a math nerd. If you're good at math, you'll eat this right up. If you're not, please keep up with the homework. That is my warning. All right? Momentum. Lesson 1, one-dimensional momentum and impulse. One of the most important concepts in physics is the idea of momentum. As a matter of fact, Sir Isaac Newton never said F equals ma. He gave his forces equation in terms of momentum. It was more important to him. He called the product of mass and velocity quantity of motion, but we call it momentum. So momentum is mass times velocity. The heavier an object is, the more momentum it has. The faster an object is traveling, the more momentum it has. The objects that do the most damage are heavy and fast. They have a lot of momentum. We would love to use the letter M for momentum, but M is already taken by mass and meters. So because it's a motion product, we use P for product. That's actually a lie. It's from a Latin word, but I'll say P for product. We get this. Momentum P equals mv. And Manny, you may have noticed that I was much more careful with my vector notation. Because momentum is a vector, I'm going to try and emphasize that to myself as a reminder all the time. You're going to see I'm going to be using the vector symbols all the time. I won't take marks off if you don't, but I'm going to encourage you, get in that habit just to consciously remind you and subconsciously remind you, please be careful with directions because they matter now. What makes momentum so important is the fact that, like energy, momentum is a conserved quantity. In an isolated system, a system where there's no external forces, the amount of momentum before an event equals the amount of momentum after an event. Momentum remains constant. Momentum is conserved. This is the law of conservation of momentum. Any moving object has momentum. Momentum is calculated by multiplying the mass of the body by its velocity. So here it is. What would the units be? Well, what do I measure mass in? Hello, what do I measure mass in? Kilograms. What do I measure velocity in? The units for momentum are kilogram meters per second. They haven't shortened this one. I know for about a decade they have been talking about renaming that an Einstein, but it's a bureaucracy in the science world, and it'll probably be 15 or 20 years before that actually becomes official. Because we've shortened other units, right? A Newton is really a kilogram meter per second squared. A joule is really a Newton meter. Most units, a volt is really an amp ohm. Most units are shorter versions. They haven't done this one yet. Yes?
Momentum means that mass has velocity remains constant. That means there can be no acceleration, right?
Careful. The total momentum in a situation remains constant. But because it's a vector, weird things are going to happen. Can you hold that question for a second? I'm going to come back to it in a bit. Okay. Here is the key idea, though. Good segue, Josh. Momentum is a vector quantity. The direction is the same as the velocity, because mass is a scalar. When you add momenta, you have to use vector addition, which means either positive is forward and negative is backward, or if you see angles, tip to tail and components. Okay. Newton's second law, F equals ma, can actually be rewritten in terms of momentum, and this is going to be kind of coming back to your question, Josh. F equals ma, I can also write that as F equals m delta v over delta t, because that's really the definition of acceleration. By the way, what does the delta stand for? What's change in anything? So this is really mv final minus mv initial all over delta t. Is that okay? I went final minus initial and I multiplied the m onto both of them. What is mass times velocity? I just set it up in the box here. Momentum. So another way to write this would be momentum final minus momentum initial over change in time. And I'll put the vectors in to remind myself there's a vector. Is that okay, Vigas? What's change in anything? So what's final minus initial? Yes, what? Here is how Newton wrote his law. He wrote F equals change in momentum over change in time. Josh, the momentum of a single object can change, which is why we can accelerate. But if you're looking at a group of objects before an event and the same group of objects after the event, the total amount of momentum before and after must remain constant, which means if one object decelerated, probably the other object accelerated, but it varies depending on the masses. Okay?
If you have a vacuum and in a vacuum one object that accelerates, there's nothing you can bump into to slow down.
Yep.
Which is accelerating it faster.
But there would be a momentum change in that event, and I'll show you an example of that in a little bit. I missed this. Needed somebody to keep me on task. Newton's second law can be stated in words in terms of momentum. So in English, we said Newton's second law, it's the mass times acceleration is the force, the unbalanced force. If you want to phrase it in terms of momentum, if you have an unbalanced or net force acting on a body, that changes its motion so the rate of change in momentum is equal to the unbalanced force. Momentum is mass times velocity. Momentum is mass times velocity. Change in is final minus initial. Impulse. Impulse is defined as change in momentum. Clay, what's another word for impulse? Change in. Max, what's another word for impulse? What's another word for impulse? When I say impulse, what am I really asking you to find, Trav? Okay. Or if I ask you to find the change in momentum, I'm also asking you to find the impulse. They're interchangeable. And I say that because I'm telling you right now, on your test, I will say find the impulse. And every year there's kids that freak out. What I really just told you to do is find the final momentum, find the initial momentum, and please go final minus initial. That's what I really told you to do. But it's way easier to call it impulse. Those of you that are Star Trek fans, they call them impulse engines. You weren't changing the mass of the Enterprise. What you were changing is the velocity of the Enterprise. You were changing its momentum. That's why the impulse engines were used for maneuvering. Warp was used for traveling through space-time. Hashtag nerd trivia. By the way, if I take this equation here and I rearrange it to get the change in momentum, the impulse by itself, if I multiply the delta t over, I get this equation. These are the only two equations for this whole unit. If you look on your formula sheet, you have this, and you have this. That's it. Yes, I think? Nothing else there. There, we're done. Your test will be next class. Well, no. All the rest of this is going to be showing you different ways to apply this. Different ways we can use this. There's several ways that you can change the momentum of an object. You can have a large force acting for a short time, sledgehammer. Small force acting for a long time. NASA is trying to invent ion engines. An ion engine for its spacecraft would shoot small atomic ions out the back. But if you did that for a long, long time, even though they have a really small mass, you'll just constantly accelerate with a really small acceleration. But if you keep accelerating for a month with a really small acceleration, you're going to be going pretty fast by the time that's done. Oh, the biggest impulses are exerted by a large force acting for a long time. What's an example of that? I don't have a good one off the top of my head. What are the units for momentum and impulse? Well, momentum has the units of mass times velocity, which is kilogram meters per second. Impulse, which is force times time, would have units of Newton seconds. Except a Newton force is what times what? So a Newton is really a kilogram meter per second squared, and then times second. Yes? And you may cleverly notice, oh, that second cancels with one of those seconds. Actually, a Newton second is the same as a kilogram meters per second. They're both measuring momentum. I don't care which one you use. I'm a nerd, Nick. If I happen to use the force times time equation, I'll probably give you my answer in Newton seconds. If I happen to use the mass times velocity equation, I'll probably, just without thinking about it, give you my answer as a kilogram meters per second. But I don't care which one you guys use. I won't be that fussy. Okay? Momentum can be expressed in either units, Newton seconds or kilogram meters per second. So can impulse. So this brings us to the law of conservation of momentum. It says this: the total momentum of an isolated system of objects will remain constant. The amount of momentum before equals the amount of momentum after. Yep.
But it just can't really basic consequence law of energy, right? Because kinetic energy, that's the same.
No, kinetic energy is not conserved. Total energy is conserved. Kinetic energy is not conserved. In fact, you're going to find the law of conservation of momentum, although it's more difficult because it's a vector, is far more universally applicable than the law of conservation of energy is always true. But remember, I always had that heat fudge factor that I often had to include to make the numbers balance. And kinetic energy is not conserved. In any car accident, you've lost all of your kinetic energy. There was a lot of kinetic energy beforehand, but afterwards, all the kinetic energy must have been turned into heat and sound. So kinetic energy is not conserved. Total energy is conserved. Total momentum is conserved. But momentum, there's less forms of, and so it's a more universally applicable equation.
Does it mean you can transform kinetic energy?
Yeah, kinetic energy can get transformed into potential energy. Watch. There.
But then momentum is gone.
Momentum and energy are not the same thing. Just hold your thought. Keep going, okay? I should say, Josh, you may have noticed I'm paying way more attention to vector notation than we have been for the last while, because energy was a scalar. We got pretty sloppy. Momentum problems, there are often changes in direction, and so we have to use precise vector analysis. For example, example 1. Next page. Momentum is used, it's a great tool to analyze car crashes. Because, Josh, in a car crash, kinetic energy is not conserved, and potential energy is, in a real car crash, most of your energy goes into heat and deforming the metal. That's where most of it goes, and we can't calculate that very easily. But momentum can be calculated. So here's a car crash, and here's the question. I said this: if conditions, first of all, afterwards, how fast is the truck moving? Look at the picture. How fast is the truck moving afterwards? How fast is the car moving afterwards? Since momentum is mass times velocity, what's the final momentum of the car crash? Momentum final is 0. How the heck can I say that there was 0 momentum beforehand then? If they're moving beforehand, so here's the question. If the conditions are such that the car and truck end up at rest after the collision, how can we say that we didn't lose momentum? I think the truck was moving at 10, and the car... No. You ready? Here's what we have. We have momentum of the truck and momentum of the car. But Clay, this is important. They are vectors. Momentum is what times what? That's one worth memorizing because it's one of only 2 equations in the unit, which means you're going to be flogging it to death. Momentum is what times what? Mass times velocity. So this is going to be mass of the truck, velocity of the truck, combined with mass of the car, velocity of the car. Let's plug in numbers. Clay, I'm going to come back to you. What's the mass of the truck?
2,400 kilograms.
What's the velocity of the truck?
10 meters per second.
Plus, what's the mass of the car?
1,000 kilograms.
What's the velocity of the car? Be very careful.
20,
No.
Negative 24.
Why? Because momentum is a vector, and they're going in opposite directions, and we have to now take that into account. And I cooked these numbers on purpose, but you can see we get 24,000 plus negative 24,000. What was the amount of momentum before the crash? 0. What was the amount of momentum after the crash? 0. Momentum was conserved. We didn't lose or gain any. Okay. Pardon me?
It would just stop, and it would need
Yeah, this would have been a car crash where each vehicle had identical momentum, and so it was enough so that they did that. Okay? That won't always be the case. In fact, let's look at some more interesting ones. So the law of conservation of momentum can be written in several ways. You can write it in English. The total initial momentum of a system equals the total final momentum of a system. Am I going to write it in longhand English? Hopefully you know me enough to know no. You can write it as the momentum of the first thing initial plus the momentum of the second thing initial equals momentum of the first thing final plus the momentum of the second thing final. You could break momentum, since momentum is mass times velocity initial, mass times velocity final. I prefer actually this one because it's the shortest and the most flexible. In fact, this VCAS is going to be my free body diagram of this unit. This is going to be my, is there a change in height, is there a change in speed, is there a curvy path, conservation of energy of this unit. This is going to be my T-table of this unit. Except we have to talk about what the heck that symbol means. Who knows what that symbol means? Yeah.
Sigma, it means changing.
It doesn't mean a change in. Change in is delta. It is a sigma, though. It means the total or the sum of. So here's what you're saying in that statement. The total momentum before always equals the total momentum after. And then from there, I'll break it down to my needs. Let's look at an example. Oh, we use conservation of momentum when there is a collision or an explosion. I'm going to say that again, but I'm going to emphasize it differently. We use conservation of momentum when there's a collision or an explosion. I joke with my students, when there's a jeune, we use conservation of momentum. Use it when there's a jeune. We use conservation of energy when there's a change in height, change in speed, yucky curvy path. This is a job for a free body diagram when there's friction and mu and forces and acceleration. You got a collision, you got an explosion, that's a job for conservation of momentum. Example 1. A rifle bullet of mass 0.06 kilograms leaves the muzzle with a velocity of 600 meters per second. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil when the bullet is fired? I would argue that firing a rifle counts as an explosion. This is a job for conservation of momentum. I'm going to start out by saying the sum of all the initial momentum equals the sum of all the final momentum. That'll get you 1 mark. And then now I break it down. Before the explosion, what was moving? The gun, the bullet, both, or neither? Before the explosion, before you pull the trigger, what was moving? The gun, the bullet, both, or neither? So how much momentum was there before the explosion then if nothing was moving? Bang! We pull the trigger. After the explosion, what's moving? The gun, the bullet, both, or neither?
Both.
Stuck together or separate?
Separate.
So I'm going to go momentum gun final. Did I say, you know what? I said rifle, didn't I? Let's use an R. Plus momentum bullet final. Then I always ask, are there angles in this question? Are there norths and souths and 30 degrees west of, nothing like that? If there was, my next step would be to dope. And I'd draw a triangle, and I'd go tip to tail, and I'd do vector math. Kyle, are there angles here? Then we're just going to decide to let one direction be positive, how about that way, and one direction be negative, how about that way, okay? So we can break this down further. Momentum is what times what? Mass times velocity. So the momentum of the rifle is going to be mass of the rifle, final velocity of the rifle, plus the momentum of the bullet is going to be mass of the bullet, final velocity of the bullet. What's this question asking me to find? Oh, okay. I think my next step, I would go minus MBVB. I would minus the bullet over to the left-hand side where there was a 0. Vince, what did you say we're trying to find?
The velocity of the rifle.
How would I get the VR by itself?
Divide
Divide which mass? Because there's 2.
M rifle.
Rifle, yeah. So if I hear you correctly, and I think I do, you're telling me the recoil velocity of the rifle is going to be, I guess is going to be a negative. What's the negative telling me? The rifle goes in the opposite direction of the bullet. Yes? Mass of the bullet, velocity of the bullet after the explosion, divided by the mass of the rifle. And now we plug and chug. The recoil velocity of the rifle is going to be negative. Mass of the bullet, 0.06. Velocity of the bullet, 600. Divided by velocity of the rifle, 3. Oh, I should be able to do this in my head. 600 divided by 3 is 200. 12. 1.12. Negative 12? Double check me. Yeah. This rifle's going to go backwards pretty fast. By the way, I made it a very heavy bullet, and 600 meters per second, well, 330 meters per second is the speed of sound. This bullet's going almost twice the speed of sound. This is a bullet with a lot of momentum. And the gun doesn't weigh much. And the bullet, a 60-gram bullet, that's a pretty heavy piece. Yeah.
Isn't it velocity? So it was just.
Oh, ooh, thank you. I did momentum.
I think that's just.
That's a candy. I'll get you one later. Good catch. Here. No one noticed. Okay. Let's try another one. Football. Hey, football tackles, American football tackles, are collisions. They're great examples of conservation of momentum. So, example 2, part A says, what is the momentum of a 112 kilogram football player running at 4.8 meters per second? Okay, this question isn't talking about a, you know what does this question want me to find? Just straight momentum. Okay. Momentum equals mass times velocity. Did they give me the mass? 112. Did they give me the velocity? 4.8. What's the momentum of this football player? 538, 537.6, but I'll go to 3 sig figs. 538 kilogram meters per second, and I'm going to add an arbitrary direction. I've watched football Kiowa. Generally, they tend to run forward. There's my direction. So let's say this is a running back carrying the football. Okay? What impulse must a tackler impart to the football player in part A to stop him? What's another word for impulse? Change in momentum. What change in momentum does the tackler need to impart in order to stop him. You can do this without calculating anything. Now, there's two ways a football player can do this. If the football player has a smaller mass, he's got to be running faster to bring the guy to a stop. Those are your cornerbacks and your safeties. If the football player is a lineman with a big mass, say 150 kilograms, he doesn't need to be going as fast. In fact, he can be barely moving at all and still exert enough impulse to bring the guy to a stop. Now, we are assuming head-on collisions because at this stage, that's all we can handle. We will get into angles at a later date. Okay? But this also explains, Mitchell, kind of why the players of different masses play the positions that they do. Every once in a while, you'll get a freak. You'll get a running back who doesn't have the mass of a normal running back, who's got the mass of a linebacker. The one I remember from the 90s, if you're a football fan, some of you might remember there was a running back for Kansas City called Christian Okoye. Nickname was the Nigerian Nightmare, because he was about 6'5", weighed about 260 pounds, but he could run like a little 5'8" running back. And for 3 years or 4 years, he terrorized the NFL. He led the league in rushing a couple of years, and he was a freak. The problem is, though, human physiology, your joints are not meant to take those kind of impulses, those kinds of changes in momentum. And so by his 4th or 5th year, he'd have permanent knee damage, and he ended up playing for like 5 or 6 years and then gone. Rarely do you see a physical that kind of anatomical specimen where they got the big muscles, the big mass. Your joints can't handle it. As a basketball fan, I'm amazed LeBron has lasted as long as he has, because we've never seen somebody that big, that muscular, who also moved that fast and put that much pressure on their joints. They don't come along very often. So some football physics for you. I can't remember who are my football players here, but some of you are, I think. C. If the tackle is completed in 1.2 seconds, what average force must the tackler have exerted on the other player? What's this question asking me to find? Force. Now, up until now, whenever we've said force, our first inclination has been F equals ma, free body diagram, except what did I find in part B? I have an equation that has force and impulse in it. It's the only other equation in this unit. It's this one. Force times change in time, impulse equals change in momentum. Impulse equals impulse. Oh, did they give me a time in this question? That's how I know to use this version to find force. Okay. Looks like the average force is going to be the impulse divided by change in time. It's going to be negative 500, and I'll use the actual number, 537.6 divided by 1.2. And I get, oh, that's a nice, works out evenly. Exactly negative 448 newtons. What's the negative telling me? If this guy is running forwards, I better apply the force backwards. If this guy is running north, I better apply the force south. Okay? And that's also why the impulse was negative. It's saying you need to remove that much momentum from this player to bring him to a stop. What if I bring him to a stop quicker? What happens to the amount of force the player feels? These are the big blow-up hits. The coming across with the shoulder and bringing the guy to a stop with a big hit, huge force. Unfortunately, of course, since forces come in pairs, you can't exert a force on a running back without experiencing the same force. But ideally, you can channel it through your shoulder pads and into his sternum, say, because you can choose where the force is applied, right? Your dream has come true. Kiowa, you're an astronaut. And you're doing a spacewalk outside the space shuttle. Oh, I missed the space shuttle. With no cable between you and the shuttle, you're using that fancy schmancy jetpack that they built. Except The jetpack has malfunctioned. Your rocket pack suddenly quits on you, and you're stranded in space, you're stationary, you're at rest relative to the space shuttle, with nothing but a $50,000 camera in your hands. How can you get back to the shuttle? In fact, to be more specific, in the opposite direction of the... Yeah.
So if he's using Martian and would he actually be able to do that with his dad?
No. In fact, in the book, he rejects that as being stupid science. You're talking about the Martian and Mark Watney, and in the movie, he cuts his finger and does Iron Man. In the book, he proposes that, and the commander says, "You're nuts, there's no way you could channel the thrust." And he says, "Yeah, you're right, it would never work." It's one of the few times they went away from the science of the book.
Then how did it happen in the book? How did he get away?
They actually rescued him normally. By the way, in the book also, the commander wouldn't leave her post to go rescue him. Not a chance. The astronaut that was trained for the rescue would go rescue him. Read the book. It's a good book. Okay? Now I can go back. You were talking about a spaceship. If the spaceship is accelerating, I'm telling you, the way that it's accelerating, it's ejecting mass out the back. That's the only way that it can be accelerating. And because it's ejecting mass out the back, there is a mass times velocity going out the back, a change in momentum going backwards, which gives you a change in momentum going forwards. That's how all rocket ships work. They all have to eject some type of mass out the back. This is a problem. Because if you bring a rocket with you and you have to eject mass out the back, that means you're also having to bring the mass with you, which means you need more fuel to leave the Earth, which means you just brought more mass with you, which means you need more fuel to leave, which means you just need more. So NASA is trying to find ways around this. In the movie The Martian, they're using what they call an ion engine. They're using a nuclear reactor, and in theory we can do this. We're working on this right now. They're using a nuclear reactor to do a matter energy transformation, and then they're firing ions of argon out the back. And because they're firing a small amount of mass but doing it continuously over a period of several months, you can still get a big small acceleration but a huge speed by the end of it, and you'd have to bring less mass along the way, is the theory. Did I answer your question okay? Good. Knew I was getting there. In fact, here's my rocket question. A rocket expels 1.2 times 1,200 kilograms of gas each second, and the gas leaves the rocket with a speed of that. Will the thrust produced by the rocket be sufficient to lift it if the force of gravity on the rocket is 5.8 times 10 to the 7th? This question here wants me to find thrust force. Now, we could probably do this with F equals ma and winner minus loser, but let's see if we can do this using force and impulse. Let's see if we can go impulse equals impulse. Could I get the F by itself? Yeah? How? Divide by the time. And impulse, what's another word for impulse? Change in momentum. What's change in anything? So on the top, do you mind? I'm going to go final momentum minus initial momentum.
What's the smallest thing that
That's supposed to be a delta. By the way, because time is always a change in, we get lazy and we often just stop because time is always a change in. And so you'll notice, Josh, I am sloppy that way. I almost always forget putting a delta in front of a time because it's always a change in. It's kind of a laziness. And momentum is what times what? Okay, so this is really going to be mass v final vector minus mass v initial vector all over time. What mass? The mass of the gas that's being ejected. What's the initial velocity of the gas? I've seen rocket engines, the gas starts out at rest. Then you ignite it. Okay? So if I want to calculate the thrust force, it's going to be the mass of the gas, 1,200, times the final velocity of the gas, 5 times 10 to the 4th, divided by, how much time has elapsed here? They snuck it in, but they were sneaky. What's the time in this question? What? Each second. That was mean of them. They didn't give it as a number. They wrote it out in English. But the nice thing is I'm dividing by 1. Heck, I can do that. In fact, you know what? I think I can do this in my head. Well, I know that 5 times 12 is 60. And then I have 1, 2, 3, 4, 5, 6 more zeros. I think you get 6 times 10 to the 7th newtons, which is enough thrust. Barely. In fact, I can tell you what the difference is. I could now, if I wanted to, go winner, thrust, minus loser, gravity. I could even calculate the acceleration and all sorts of stuff if I really wanted to, but yeah. Is that okay? By the way, this was not a collision or an explosion, and specifically they were talking about force and thrust, so I didn't go the sum of all the momentum equals, I didn't use conservation momentum. Example 5. What's the last word in example 5? This is a job for conservation momentum. I'm going to start out by saying the sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what's moving? Oh, you know what? Look up. How about let's call this mass A, let's call this mass B. There's my high-tech system. I'll figure it out if you label it like that. Before the collision, what's moving? Mass A, mass B, both or neither? So it's going to be momentum of object A initial. Wham! They collide. After the collision, what's moving? Mass A, mass B, both or neither? Both? Stuck together or separate? Then I'm going to go momentum both final. If they were separate, I would have gone momentum A final plus momentum B final. But they're stuck together, so they'll, okay. Now I always pause here. Any angles, anything like that in this question? Okay, then I don't need to worry about dulping. I'm going to break this down further. Momentum is what times what? Dustin, you're right, loud and proud. So the momentum of A initial is going to be mass A V A initial, yes? And I guess the momentum of both is going to be the mass of A plus the mass of B V final, because they're stuck together. If they're stuck together, they must be traveling at the same velocity. No angles, no trig? Oh, what are we trying to find here, Dustin? Which is which variable in this equation? I know it's AV. Which one? There's your hint. What does after imply? I want that by itself. Okay, how would I get that by itself? There's a bracket next to it. What's the bracket doing to the VF? Adding, subtracting, multiplying, or dividing? So how will I move it over? You say? Hopefully we're kind of in familiar territory now, yes? Cool, 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 cool. So if I hear you correctly, Dustin, I think I do, you're telling me that the final velocity after the collision is going to be the mass of object A, velocity of object A initial, divided by the mass of object A plus the mass of object B. Now before we go further, what if object B was heavier? What would happen to their combined velocity after the collision? Bigger, smaller, or stay the same? What if object B was heavier? Be smaller. Yeah, if you run into a bus versus if you run into a truck versus if you run into an Austin Mini, in all of those, if you stick together, your velocities are going to be different. And I'm going to suggest if you hit a bus, your combined velocity afterwards isn't going to be big at all. Might even be close to zero. Okay? Or, what if car A was traveling faster before the collision? What can you tell me about their velocity after the collision? Bigger, smaller, or stays the same? Bigger. This is why car crashes at higher speeds do more damage. Oh, yeah, I guess that makes sense. Okay. Let's plug and chug. Final velocity is going to be 3.2 times 1.2, all divided by 3.2 plus 1.8. Do it. You might be able to do this one in your head. Because 3.2 plus 1.8, that's 5. Sure. I factor it. No, hang on. That's yucky. No, maybe. 3.2 times 2.4 is going to be... no, I haven't got it. I'm not back in mid-season form yet. Is it 0.768? 0.768 what? Units? Meters per second. Direction, in the same direction that cart A was traveling. In the same direction as cart A was traveling. Okay.
What is that in kilometers an hour?
0.768. If you double it, that's roughly miles an hour. So it's only about 1.5 miles an hour. In kilometers per hour, you would times that by 3.6. So even that, it's about, well, 0.8 times 3, it's about 20 kilometers per hour, give or take, maybe a bit more.
You mean two?
Sorry? 2. Yes, I forgot. Yeah, sorry. I carried an extra 0.
So that's half the speed you're going.
Suppose a railway car is coasting along the track at 7 meters per second, and then suddenly an extra load of coal is dumped into the car. The car will slow down. What's its new velocity? This is a job for conservation of momentum, but I'm going to skip it. Example 7. What word did I underline? What are they asking me to find? Read carefully. What are they asking me to find? This is a job for conservation of momentum. There's a collision. They want me to find the velocity. Oh, yeah. Conservation of momentum. So, the sum of all the momentum before the collision equals the sum of all the momentum after the collision. So here's an example of a car crash. A 1,200, oh, you know what? Let's call this car A. Let's call this car B. A 1,200 kilogram car traveling 33 meters per second collides head on with a 1,900 kilogram car traveling 24 meters per second in the opposite direction. They're going to stick together. We don't have to, by the way, but in this case I decided to make them stick together. Okay. Before the collision, what's moving? Car A, car B, both or neither? Both stuck together or separate? Before the collision, stuck together or separate? Okay, so it's going to be momentum car A initial plus momentum car B initial. Wham! They collide. Mr. Dewick, are you going to do that for every single collision? Maybe. After the collision, what's moving? Car A, car B. By the way, the reason I'm asking what's moving is if it's not moving, what momentum does it have? 0. I just ignore it. So after the collision, what's moving? Car A, car B, both or neither? Both? Stuck together or separate? Okay, so momentum, both. Final. Pause. Pause. Any angles, any north of south, east of west, any weird thing there? If there was, I would now dulp, and I would carefully be adding stuff tip to tail. We will get to those in a couple of days. But since there isn't, I can break this down even further. Momentum is what times what? So this is going to be mass of car A, velocity of car A initial, plus mass of car B, velocity of car B initial, when they collide, equals mass of car A plus mass of car B V final, because they stuck together. What am I trying to find here? V final? Oh, how would I get the V final by itself? Okay, so I think, Clay, if I hear you correctly, I think I do, you're telling me V final is going to be mass of car A, velocity of car A initial, plus mass of car B, velocity of car B initial, all divided by mass of car A plus mass of car B. By the way, I think I like this question. I think I like this question. I think I like this question. All right, let's plug and chug. Dale, what's the mass of car A, my friend?
1.2 times 10 to the
I'm going to go 1,200 because it's less writing, but yes. Was there a little flash of light there or something like that?
Yeah.
Oh, you guys are hoping. I'm not. What's the velocity of car A? 33. Plus, what's the mass of car B? 1,900. What's the velocity of car B? Careful. Why negative 24?
It's going to be option.
Now, I'm going to tell you right now, I guarantee if I gave you this question on the test and it was multiple choice, I would have the positive 24 answer there for you to pick from. Direction matters. Direction matters. Momentum is a vector. Be paranoid, Mitchell, about your directions. Divided by 1,200 plus. Now, if I get a positive velocity, then the direction will be in the direction of car A. If I get a negative final velocity, the direction will be in the direction of car B. Car B would have pushed car A backwards. If I get a positive answer, car A would have pushed car B backwards relative to car B. What do you get? You get negative 1.94 meters per second. They're almost enough to cancel out. Because if it was 0, they would cancel out. That would have been a collision that did this. Here, negative, car B wins, I guess, if we want to say that. Now, by the way, Nick, the reason I said immediately after the impact is as soon as the impact occurred, and this goes back to what Josh was pointing out, now also conservation of energy would take place. You're slowing down because of friction in the tires, because there's no way that this collision is still rolling all nice, and you'd come to a stop very rapidly. So this amount of kinetic energy, the a half m negative 1.94 squared, would very quickly get transformed into heat and friction. Sound. Baseball is also a good example of a collision. Yes?
Just like in general, if you want to get a high momentum,
Yeah.
it would be the same to accelerate for 3.6 kilometers per hour, or just gain 1 kilogram weight.
Lose 1 kilo. You want a higher momentum? Oh, okay. Not a higher speed, a higher momentum. If you added 1 kilogram of mass, that would be the same as a change in velocity. Well, no, it'd be the same as a change in velocity of 1 meter per second, which is that 3.6 kilometers per hour? I guess. For 1 second only, though, not more. Baseball. Hitting a baseball with a bat is sort of a collision. Although, wait a minute. Although there is a collision here. Mitchell, what's part A asking me to find? Nice and loud and proud. What's another word for impulse? Okay, put your pencils down, look up. There's 2 ways to find impulse. This way or this way. So Mitchell, before we find the impulse, we have to decide which one of those we're going to use. So I'm going to look at the data that they gave me here. Did they give me a force and a time in part A, or did they give me a final and an initial velocity in part A? I'm not using that one. So pick up your pencils. I'm going to use for impulse final minus initial, not force times time. Do you see how we figured that out, Nick? Okay. So whenever they ask find an impulse, I have to ask, well, which way? If they gave you a force and a time, use that one. If they gave you 2 velocities, use that one. Mitchell, momentum is what times what? Mitchell, momentum is what times what? Mitchell, momentum is what times what? Raj, momentum is what times what? Thank you, Raj. You were ever so clever. So this is going to be mv final minus mv initial. Raj, what's the mass of the baseball? Careful. What's the mass of the baseball? Thank you for not saying it was 145 kilograms. Yeah, 0.145. What's the final velocity of the baseball? 50 minus, you said the mass of the baseball was 0.145. Raj, what's the initial velocity of the baseball? Nope. By the way, I like this question. Why negative? So if you missed that, underline north, underline south, and you'll notice, Raj, I actually, by putting that negative in there, I get a minus, which gives me a bigger change in momentum, which, you know what, hitting a baseball, yeah, because you're having to first bring the baseball to a stop and then send it back in the direction that it came. You need a big change in momentum to do that. The impulse, the change in momentum, is going to be 0.145 times 50 minus 0.145 times negative 40, 13.1 kilogram meters per second, or Newton seconds. Now, Max, if you decided to let north be negative, if you let V final be negative, and you let V initial be positive, you would get an answer of negative 13.1. I would give you full marks for that, because I would just look and see if you were consistent in your work. Okay. Usually, I'll tend to let the final be positive if there's a change in direction, because, Raj, that usually gives me a minus, and I like it when negatives cancel, because the math usually gets cleaner. That's me being really pedantic, though. Trav, back row. What's B asking me to find? What did I find in part A? Is there an equation that has force and impulse in it? Hey, yeah, I'm not going to go F equals ma. I'm going to go force change in time equals change in momentum. I'm going to go impulse equals impulse. How could I get the force by itself, my friend? So if I hear you correctly, and I think I do, you're telling me the force is going to be the impulse divided by the time, which is going to be 13.1 divided by how much time? 1 millisecond. What the heck is milli? 10 to the what? Hey, that's on your formula sheet somewhere, too, isn't it? Is it negative 3, I think? Yeah, -3. I think 13,100 newtons. And if you wanted to add a direction, since I got a positive answer, the force must be applied to the north, since that's what Raj let be positive. Okay. What if I want the baseball to leave the bat even faster? What if I wanted the baseball to leave at 60 meters per second north? Well, I better exert a bigger force. I better hit the ball harder, which again seems really obvious because you played sports, but there's the physics behind it. Oh, what if I don't want the ball to leave very fast at all? Well, here's the physics of a bunt. I try and make my force exactly equal so that my change in momentum ends up canceling out the baseball, but having a V final of 0. There's your bunt. Or if you want to send the bunt down the batting line, that's also different as well. Down the baseline. It's kind of cool, but I'm going to skip it because I've had it. I'm going to snap. Here's the same kind of question. 2 eggs are dropped from a height h. One egg hits the floor and breaks. The other egg lands in a pail of water and survives. What's the main reason the second egg survives? They have the same mass. Their initial velocity is the same, 0. Since they're being dropped from the same height, their final velocity is the same. So I am going to say they both go through the same change in momentum, the same impulse. Why does the egg in the water survive? Which variable have we changed? Time. We have 2 choices. We can have big force, little t, or we can have small force, big T. Is that clear, writing it that way? By the way, this is all seatbelts do. The original seatbelts actually just stopped you instantly, but if you look now, modern lap belts have a bit of give before they bring you to a stop. They're desperately trying to lengthen the collision time, because if we can lengthen the collision from 1 millisecond to 4 milliseconds, which isn't that much time, we've dropped the force on you by a quarter. We've divided the force on you in 4. That's a huge difference in survivability. If we looked at a graph of force versus time for the egg hitting the floor, it would look like this. By the way, what would the area underneath this graph be? What? What was the trick I told you to figure out an area? Either multiply the variables. Oh. Or you actually did the units. I usually do the variables first because I'm familiar with the equations, and then my fallback is I'll try the units. But yeah. You know what? The area underneath this is the impulse. So with that in mind, which of the graphs, A, B, or C, would best represent a force versus time graph for the egg hitting the water? Then it says the egg on floor graph is shown as a dashed line. That's not appearing anymore, is it? So I should scratch that out. Over time, this diagram has degenerated. Which of those do you think would match the egg in the bucket? A, B, or C? Why C? You're right. Why C? First of all, why is A wrong? Because I think the time of the collision is the same, and we know that's not the case. Right? What about B and C? I think B has too big a force still. It's going to be C. I apologize. My lesson went about 10 minutes longer than I planned. But what's your homework? Number 1, no, you need to practice this. I'm sorry, but you do. Number 1 is good. 2 is good. I like number 3. I like number 3. I like number 3. Skip 4. 5 is good. 6 is good. I'm going to skip 7. I like number 8. I like number 8. Number 8 is a nice question. Nine is good, collision. 10 is good, collision. Skip 11. 12 is good, collision.
Okay, it says $5, 14 or not.
Yeah, that's what I think too.
14, 15, and 16.
Never should have thought.
And those answers to 14, 15, and 16 I put on the next page there.